Hi there, Physics 131. This is the pre-class video for class 32. We're continuing on in chapter 11 here. Section 11.4 is called Energy, Power, and Intensity of Waves. And it is a little brief, and there's a few things about the energy and intensity of waves that's going to come up in subsequent sections. So I'm going to jump around this chapter 11 a little bit here. But certainly there's wave amplitude is sort of what we're talking about here. If the amplitude is more, then you imagine that there's more energy being carried by the wave. So she talks about energy a little bit. There's a little bit of talking about how if there's such a thing as a two-dimensional wave, I guess on the surface of water, then the energy would decrease as 1 over r. But in this course, we're really going to talk more about sound waves and the light waves when we get into Physics 132. So the much more important equation deals with three-dimensional waves, and it's this one. So this is what I like. The energy per unit area per unit time passing across a surface perpendicular to the direction of the wave travels decreases as 1 over r squared, where r is the distance from that point to the source of the wave. So that is called the intensity of the wave, and she doesn't introduce it as that there, but talks about energy. Intensity is energy per area per time. So that's what this means when you go through this example of the cicada. Now I want to quickly just jump ahead now to section 11.7 on sound. So it talks a little bit about the eardrum and things. There's an example here though I want to draw you to. So here it is. Quantitative exercise 11.5 talks about sound at a construction site. So the intensity of sound at a construction site is 0.1 watts per meters squared. That's exactly this energy we've just been talking about. And then it says if the area of an eardrum is 0.2 centimeters squared, how much sound energy is absorbed by one ear in an 8-hour workday. So that's where this intensity of the wave, sound wave, is coming from. Its intensity is energy divided by time and divided by this cross-sectional area. So an area that's perpendicular to the direction that the sound wave is traveling. So that's intensity, and you know that it's 0.1 watts per meter squared. If you want to find the amount of energy, delta E, that your ear absorbs over some amount of time, you take that intensity, multiply it by the 8-hour time, and multiply it by the area that your eardrum takes up, which is less than a square centimeter. So you get 0.058 joules. This looks like a small number. However, our perception of sound energy depends on power per unit area, not the total energy. So it says that our environment includes sounds that differ from about 10 to the minus 12 watts per meter squared, barely audible, to nearly 1 watts per meter squared. So this is a difference here of 10 to the 12. That's 1 trillion times different between barely audible and painful sound. So this is what leads us, and I'm still in section 11.7 here, sorry about that, but this leads to intensity level, which is this new thing, beta, is 10 times the logarithm, base 10, of intensity divided by some reference intensity. So the reference intensity is this 10 to the minus 12 watts per meter squared. And then for different intensities, if you take the logarithm of that, you get this number and multiply by 10. Like for example, if it's 10 to the 6 watts per meter squared, that's a decibel level of 180 decibels. That's that beta. And I think the logarithm of 1 is 0. So the 0 decibels would be that hearing threshold, the barely audible sound. This 1 watt per meter squared, that's the rock concert. The pain threshold of pain is 120 decibels. That means it's 1 trillion times more intensity than this one. So that's sort of skipping ahead. Going back to section 11.5 on reflection and impedance. So we did talk about reflection of waves a bit before, when the rope was attached to a wall as opposed to attached to a ring that could slide up or down. So this is talking about impedance here. So you could have a thin rope which is attached to a thick rope. So something has changed about the medium here. It's gotten, I guess, to be a thicker, slower medium. When that happens, and you say that this is like a higher impedance medium, then it's a little bit like bouncing off a fixed wall. You have a reflected pulse which is inverted relative to the original pulse. The difference here is that with the thick rope, higher impedance, slower medium, you also get a transmitted wave. So there's actually 3 waves. There's incident, that's the first wave, and then it splits into 2. It splits into the reflected and the transmitted. Okay, and then the same thing happens when you go to a lower impedance medium with a higher speed, a thick rope to a thin rope. What happens here is it's similar to when you have the ring, the sliding ring. So you have a reflected wave which is the same direction as the incident wave. So the incident wave comes in and splits into a positive reflected pulse and a positive transmitted pulse. And there's usually a higher amplitude on the transmitted pulse there. So that's a little bit just about reflection and impedance. So definitely kind of read through that, and I'll talk more about it in class. Bye for now.